This is Tennin Yan from QunaSys. That we are a startup based in Japan. So today I will talk about quantum algorithm and software development in QunaSys. So first, I will have the brief introduction about us. So we are a company founded in 2018, and currently we have 9 employees, including 6 PhD. And we are a company co-founded with the Keisuke Fuji, who is the famous quantum information researcher in Japan. And he's like one of the reviewer of the Google quantum supremacy paper. And what we are focusing on is the developing quantum algorithms and software, and we are especially focusing on chemical calculation using the quantum computer. So what we are offering is the two things. One is that doing joint research. So quantum computer currently is not powerful enough. So we have to think a clever way to utilize these devices. So it will be really important to search for new algorithms utilizing the quantum computer. And the second is that since there are a lot of algorithms developed in the quantum computing field, that it will be quite difficult to user to understand what is the potential application for them, what is the good algorithm for them to use. So we have the software tools that user can easily test the algorithms that we developed. So I will go to the topics that first that to talk about why the chemistry is the promising application. So I think as you know that this is the famous slide by the BCZ that it is considered that the nearest potential application of the quantum computer is the chemistry, and it has a really high impact. And what we think is that there's a high possibility that doing the machine learning or doing optimization, we need a fault-tolerant quantum computing device which needs 10 years, but we think it's quite promising that using the currently NISQ devices that we can do the chemistry calculations. And also we are currently working on doing the pharma simulations using the NISQ devices. And this is as the Feynman said, that the simulation of the nature, we need the quantum computer, quantum mechanical device to do that. So this currently really fits the needs of the quantum computer. And so where is the target in the chemistry field? So that's the frequently asked to us, and this is kind of our answer, is that there's a lot of algorithms that a lot of chemistry calculation that currently works with the DFT calculation, which DFT stands for density functional theory. But what we think is that if your problem currently works well with DFT, and if you want to simulate larger molecules using that DFT method, that's not the application of the quantum computer. What we think is that the quantum computer using the quantum chemistry calculation using quantum computer, the potential application area is that the area that the currently DFT doesn't work. So just give you a several example is that like you do the solar energy conversion or light emitting devices, that if you want to simulate that kind of system, that you have to consider, for example, like the really heavy metals inside, and you in that sense that the DFT doesn't work. So in that area, that it will be the potential application of the quantum computer. And so I will talk about basic algorithms of the quantum chemistry on quantum computer. So this is the explanation of the really basic algorithms called variational quantum eigensolver. So first in the left side that the user usually misunderstand is that the there's if you want to simulate large molecules using the rich basis set, you need a lot of qubits to simulate that. But there's a way to limit that qubit, is that by limiting the active space you need. So in this green dot inside, that we limited the active space to 2 orbitals, and it will be 4 spin orbitals. So if you simulate this, you just need 4 qubits to simulate this. So by limiting the complete active space, that you can just use small quantum computer to simulate this. And so using quantum computer, that in by limiting this complete active space, that you include the static electron correlations, but outside this active space, you can include that effects, that dynamical electron correlation effects by classical computer. So this is the way we think that the best matches the use of the current quantum computer. And then in this active space, to calculate the static electron correlations, we run VQEs. And to run VQEs, this right side, you prepare the quantum circuit and you obtain the wave functions. And by getting the expectation value of the Hamiltonian energy, and by minimizing of the using updating the parameter theta, you can get the ground state energy. And this will be the basics of the quantum chemistry on quantum computer. To be honest, that the calculation of the ground state energy is not the only things that chemists do every day. So for example, doing reaction per search, molecular dynamics simulation, this will be really important for like the exploration of the chemical reaction or predict the dynamical informations. And and something else is that the vibration frequency analysis for the chemical spectrums and non-adiabatic dynamics, like doing the identify of the molecules or doing the photochemical reaction, these things is important. And also condensed matter simulation is also important. So I will talk about algorithms for these applications. So I will go to the what we are doing. So when we are founded like 2 years ago, there's only algorithms of VQE. But after this, we think that if we can simulate like excited states or energy derivatives or other like periodic system green functions, that will expand the potential of the quantum computer. So that's what we did, and I will briefly explain the algorithms to calculate this. So first is that way to calculate excited states. So for example, that excited states to calculate using the TD-DFT method, and that will be a lot heavier than current DFT method. And so the excited state calculation is more heavier than it'll be a lot heavier in the classical computer. So we think that if we can calculate excited states, that will be promising applications. And that there's a lot of examples that the TD-DFT won't work in the excited state calculations. So we develop our algorithm called subspace search VQE, and we also have comparison between the other method like MCVQE, VQD in our paper. And next is calculation of the energy derivatives. So if you can get the energy using the VQE, and if you can calculate the the derivatives, that like calculation of first derivatives, you can do molecular dynamics simulation and reaction route search, and also like combining with the former method to calculate excited states, you can also get the energy derivative of excited states, and using that you can simulate like conical intersection, minimal energy crossing point search. And also this the energy derivatives method we developed gives you the second derivatives, and using the second derivatives you can do vibration analysis. And next is the photochemistry. So in the right side is like there's a ground state surface and excited surface. So to simulate this kind of photochemical reactions, that you first have to simulate the transition amplitudes that gives you the possibility to of for the ground states to be excited states, and also after that, that there's a crossing point of the excited states and the ground states, and to gives that the possibility to hop from the excited state to ground state. It you need to calculate non-adaptive couplings. And in the right bottom papers currently on arXiv, that we show the algorithms to calculate the transition amplitude and non-adaptive couplings using quantum computer. And other is the simulation of periodic system. So this will be like the battery materials is normally the periodic system. And this will be really important to simulate a lot of materials. And so we developed the algorithm to simulate the periodic system. And we are currently working on combining these algorithms and with other methods to calculate of the band gap. Okay, so as I explained that we have developed a lot of algorithms, and I will from now talk about what software what we are making. And so as I explained that there's a lot of algorithms developed by us and also like other universities. So it's kind of is confusing for users. So what is the potential application for them, or if they want to simulate this kind of some like the excited states, what will be the good algorithm for them to use? So for that, we designed our tools Qamuy. So user can easily design the test they want to run, and user can easily do the benchmark of the algorithms and do analyzation. Like for example, what is the bottleneck of these algorithms? Or in the chemistry, it was really important to know that if that algorithm is reliable or not. So we also have a lot of function for user to evaluate that. So it's currently for user to important to do this kind of cycle, doing design of the experiment and do benchmark of algorithms, and then analyze if that will be useful for them or not. So we design a tool that user can quickly do these calculations. And then, of course, it will be also important to explore new algorithm because current algorithm is limited, and we also have that capability to do that. But we will talk about the design and benchmark analyzing tools Qamuy. So because I don't have time today, and we are happy to give a demo of this system if you contact us. But this is the really basics of our cloud tools Qamuy. And so in the left side, that it's really easy for user to use. The user just have to specify molecules that input the nucleic coordinates, and it gives you have the specify which the basis state they want to use, and that's the input of their molecules. And also like this, you have to input the quantum computer options, like what algorithms you want to use, or what ansatz you want to use, what optimizer you want to use. And in Qamuy, you don't have to write all algorithms yourself. You just have to specify, like if you want to use the subspace search VQE to calculate excited state, you just input SSVQE and input that data to our crowd system, and our crowd system automatically generates quantum circuit. And we currently recommend user to use simulator, and that gives you the measurement result. And in the left bottom, like for example, user can easily analyze the calculation results. And in this example, that user it compares what optimizers good to calculate excited states. So you can see that orange optimizers gives the chemical accuracy at the fastest speed. And so yeah, this is what we are making. So, and currently what Qamuy can do is the calculation of the molecular properties. So the Qamuy calculates energy gradient, Hessian, and so on, a lot of molecular properties. And to calculate, like for example, transition amplitude, there's a lot of combinations for user to use, like what excited states algorithms they want to use, or what ansatz they want to use, and we have a lot of implementation of these algorithms, and user can easily choose and compare the ansatz optimizers. And also, we currently have the state vector simulator and also the sampling simulator. And also that currently the IBM Q Premium members can use IBM Q devices from our systems. So using the Qamuy, like the combination of the, like for example, calculation of the energy and the first derivatives, and user can calculate the reaction per search, and using first derivative, user can calculate the molecular dynamics simulation. And also, like as I said, the Qamuy calculates the second derivatives. You can do the vibration frequency analysis. And yeah, using the transition amplitude that calculated by Qamuy, that you can do photochemical spectrum analysis using quantum computer, and also like combining with non-adaptive couplings and first derivatives, the user can calculate the surface hopping demo, and also user can simulate condensed matter using the Qamuy. So the key features of the Qamuy is that the first is that it's chemistry friendly interface that the user, like maybe a lot of people doing Qiskit, for example, that you have to write quantum circuit yourself, but the Qamuy is the really chemistry friendly interface that you don't need to implement quantum algorithms yourself, that you just have to specify which algorithms you want to use. And also we have, I think, we have the widest variety of physical properties or molecular properties that we can calculate. The calculation of like the gradient, Hessian, non-adaptive couplings, I think that's kind of really unique in our system. And like we have a lot of ansatz optimizers implemented. So like I calculate that totally user can do more than 100,000 quantum algorithm option combinations. So you can test a lot of combination of the quantum computing algorithms. And the other key features of Qamuy is that it's fast. So we are using the world fastest class, the quantum simulator QunaSys, that developed by our advisors, that QunaSys as a backend, and it will gives you 100 times faster in the typical size of the simulator a user using, like 10 to 15 qubits. It will gives you the 100 times faster simulations. And we have a lot of function for your research. For example, if you do the sampling simulator, that it will be the variance of the sampling. So the Qamuy gives you estimation of the statistical error. So if you do like the 1,000 sampling per Pauli, that will give you a large statistical error. If you do like the millions sampling per Pauli, it will minimize your statistical error. So you can analyze that kind of things in Qamuy. And also that we have the benchmark of the real device execution time. And even you are using the simulator, that it will gives you the expected execution time of the running that algorithms on real devices. So I will conclude my talk here. And yeah, please feel free to contact us if you want to know more details of our algorithms or have a demo of our tools coming. So that's all my talk. Thank you.